Good morning. We're STEM, which stands for System for Measurement of Evapotranspiration. My name is Jeffrey.
I'm Robin.
Eric and David.
So why STEM? STEM is a system that is significantly cheaper than our competitors, namely Tulia and S.T.E.M. We have more features than these guys have, and we have the added bonus of pushing our information onto the web. So the system overview here. The primary objective for this system is to be able to measure evapotranspiration of plants with pinpoint accuracy. What is evapotranspiration? Simply put, evapotranspiration is just the measurement of how much water a plant has taken in throughout the day and how much water a plant has lost throughout the day. So using this two bits of information, we can very carefully calculate exactly how much water needs to be added to the plant. And this is done so by measuring soil moisture levels and leaf temperature. Then we have this information, we push it online. So we have a web interface and a very slick web app. So anybody can view this online at any time. And this is our web interface. We put in information of where these sensors are located in a vineyard, and we have battery status management as well as the raw data that could be viewed with the chart here. And this is our release design. We have our main PCB over here, and this is our so-called upstairs board. On here we have connectors for our 4 soil moisture sensors. We have an infrared camera up top. We have our battery management IC up there towards the right, and we have our wireless communication module, the XP, over there. Because we really only have 3 distinct types of sensors, the power architecture is relatively simple. Everything on this device is powered off of a battery, and this battery could be recharged with a solar panel. After this battery, we can boost it up to 5 volts, which powers our soil moisture sensors. We also can step it down to 3 volts, which powers our temperature sensor and our infrared camera, as well as the main PSOC chip itself.
So this is our communications. In S.T.E.M, we see the PSOC. Most of our communication is done through I2C. So for the IR sensor, we're connecting that through I2C. And then we have our Vegetronics, which is our soil moisture sensor. That puts out ADC, and we convert that back to I2C, back to the PSOC. The thermometer sensor, our temperature sensor, is also I2C. So to communicate to our web, we have a XP. The XP is wireless to a BeagleBone, which is connected to the IP. That's our BeagleBone.
This is our BeagleBone, by the way.
Alright, so these are the sensors that we use. For the infrared camera, we use the MLX90620, which has pretty good accuracy. It's within 1 degree Celsius for the range that we need, which is enough to tell when a plant is basically opening or closing, which is what we're trying to do with the infrared camera. It also takes relatively low power, and this is, however, the most expensive sensor on the board, but that's okay because we only need 1 of them. The Vegetronics soil moisture sensor is the moisture sensor that we're using, and basically our product is going to have 4 of them that are underground at different depths to create a soil moisture profile for the vineyard. And at each depth, there's also going to be a little temperature IC that basically reads the temperature that is at each depth to effectively calculate how much water the plants are taking in.
This is our state machine. We have a mixture of inputs to this device because we are communicating constantly with our BeagleBone, which is effectively acts as a web server. So we have our sleep and wake mode, we have our get data, and we have transmit. We can also detect whether or not we have a good transmission of data or not, and that is when we can ask the device to simply retransmit. And since soil moisture and soil temperature doesn't change a lot throughout the day, we were only give it 3 chances to transmit correctly. After 3 chances, we figured, well, we can afford to drop this particular data point. The researchers won't mind too much, and we're not going to waste any more battery power before putting it back to sleep.
Alright, this is an initial analysis of power. based off of the rated power consumption of our devices. So the point that you can see here is that when we sample, which is going to be every 15 minutes, our power consumption is actually dominated by the XP. That's because it has a high transmit current. A lot of the sensors and regulators don't consume too much power. PSOC itself isn't much at all. In the meantime, when we're not sampling, we put the device to sleep, and so in that case, the PSOC is very minimal. If we shut down the regulators and shut down all the sensors, that's very minimal as well. We have a 2,500 milliamp hour battery, so with the amount of power consumption that we're using, and over the time periods that we're consuming those amounts of power, we can make it last a long amount of time. So the key to our project, since it's battery powered and it's going to be in a vineyard, is that we have to make it as low power as possible. We also have solar capability and a battery charging circuit, so that in addition to trying to, on the demand side, lower the power demand as much as possible, we can, when needed, have a supply of electricity from the solar panel. Here's our marketing video.
Shot at the golden hour, which is the important bit.
Irrigation of vineyards have become more efficient by calculating evapotranspiration, but systems that do so are expensive and complicated. This is why we developed S.T.E.M, a simple sensor network that calculates ET with pinpoint accuracy. Soil moisture probes measure how much water a plant has absorbed, and an IR camera measures how much is lost. This is wirelessly transmitted to our web app, so we can view this information in real time for your computer, tablet, or phone. A robust backend ensures that this data stays organized and available. With more information at their fingertips, vintners can make better decisions as to when to water. Soil scientists can better explore the beauty of science. And this is just the beginning. Greater connectivity allows us to more efficiently conserve our resources for future generations. So join us. The fun is just beginning.
Wasn't that great? Don't instant questions.
I mean, I guess this applies to all groups, but how did you guys manage to keep track of the power consumption for your devices?
So right there, that was just a theoretical one. So I went into data sheets and, power equals current times voltage.
And they give you the
that's all I
current
did.
consumption for
But
imitations.
so on our board though, what we can do is we put in some headers so that we can measure like the total current going through the device from the power supply, and then multiply that by the voltage, and then that way we can measure the whole supply, the whole amount of power that the device is consuming.
Question was if I consider that one reactor as one node, how many nodes can work on simultaneously on one network?
I'm sorry?
Because you are using XP to transmit your logs, so
Correct.
how many nodes can work on simultaneously?
Simultaneously, we can actually have quite a bit because the backend system for our data is called Firebase. And Firebase is really powerful in that it organizes and collects each data individually. So all we need to do is tell it exactly, because they're all transmitting in broadcast mode, we can just tell it that, well, we're just going to add another node, and we can just continue to do so indefinitely until pretty much you run out of bandwidth.
In this application, how many sensor sites do you anticipate having when
Talking to Dr. Lambert, he wishes to have as much as possible, so we're looking at 10 to 15.
Any other questions?